Hi everybody, Cal here with sections 14.6, directional derivatives and the gradient vector, and 14.7, maximum and minimum values. We're going to start here on page 597 with directional derivatives and the gradient vector, and just like with partial derivatives, I think your book does not do the world's best job of introducing what a directional derivative should be, and so let me tell you, if the derivative df dx is the change in f as x increases, and if df dy is the change in f as y increases, then the directional derivative, basically, we call it, sorry, I'm blanking here. The directional derivative d sub u of f is the change in f as we walk in the direction of the vector u. Again, I mean, this definition, I mean, it's true, but it's not necessarily the way that we want to think about the directional derivative. And we'll get to actually computing this in a moment. But what I'd like you to look at is a couple things. First of all, we need to be using a unit vector in order to talk about a directional derivative. And you can note that u in this definition is a unit vector. And secondly, I want you to understand kind of what it's saying. So example 1 is a really good example of the physical interpretation of the directional derivative. Theorem 3 tells us how we're actually going to compute the directional derivative. And we'll restate this in a moment once we have a little more language under our belt, but this is a fine way to compute the directional derivative. And again, you need to be using a unit vector in order to take a directional derivative. Example 2, as usual, you can kind of skip the proof. I mean, it's not a hard proof, so read it if you like, but anyway, example 2 is a computational example of how this works. And then we get into this discussion of the gradient vector. And the gradient vector is an important vector. The symbol that we use for the gradient is this upside-down triangle. It's usually called del, although I've also heard it pronounced nabla. I don't know what the heck that comes from. But anyway, it's a vector whose first entry is the partial derivative of f with respect to x, and the second entry is the partial derivative of f with respect to y. Example 3 shows computation of a gradient and computation of a gradient at a point. And with this notation of the gradient in mind, we can rewrite Theorem 3 from the previous page and say that the directional derivative, d sub u of f of x and y, is the gradient of f dot the vector u. And again, u has to be a unit vector in order to do this. And I would say that this is the easiest formula to use for a directional derivative. Example 4, again, shows computation of a directional derivative, and I really like example 4 because it stresses that you need to be using a unit vector. Below that, we talk about what happens with functions of 3 variables, and it's really the exact same development. We talk about the gradient vector for functions of 3 variables. It's the vector with 3 entries, and the entries are df dx, df dy, and df dz. And again, the unit, directional derivative in the direction of a unit vector u is just the gradient of f dot u. And example 5 shows a great computational example. Now, I really like this section at the bottom of page 962 about maximizing the directional derivative. And this theorem kind of gives the entire story. If f is a differentiable function, then the maximum value of its directional derivative is the norm of the gradient of f, and it occurs in the direction of the gradient vector. So I'm going to suggest that you pay some close attention to examples 6 and 7, and the drawings to the left, figures 7 and 8 to the left, they kind of illustrate what's going on with this theorem. And then we have a little discussion at the end about tangent planes to level surfaces. which gives you an alternate way to get the equation of a tangent plane when you're dealing with the level surface of a function of three variables. And this is a good formula to know and is pretty useful. I think the discussion here of normal lines is pretty much in agreement with what we know about planes. And example 8 is a numerical calculation of this new method. Finally, we talk about significance of the gradient vector, and the main idea is that the gradient vector is the vector that points in the direction of greatest change. That's what that earlier theorem said. This also means that it's going to be perpendicular to level curves, which is going to be important for us. And really, if you know those two things, then you kind of know what you need to know about the gradient vector. It's perpendicular to level curves, and it's in the direction of steepest ascent of your function. That ties together 14.6. We're going to move forward directly after the exercises into 14.7, maximum and minimum values. And this is going to kind of follow the discussion in single variable calculus. You might recall that we have what's called critical points in single variable calculus, and that's going to be in places where your derivative is 0 or undefined, or at endpoints of your domain. And in Calc 3, it's the same kind of thing. If we're looking for maxima and minima, we're interested in places where all partial derivatives are 0, or in other words, where the gradient is 0, or where partial derivatives are undefined. And we can see this in this definition right here of critical points down here. So these are an important definition, important theorem, but this should mirror things that you remember from Calc 1. Example 1 shows an example of finding critical points. And in fact, using that critical point to find that the function we have is a minimum. Example 2 is another example of finding extreme values. And what you'll notice here is that classifying critical points as local maxes, local mins, or as neither, what we call saddle points, is a little more complicated than it is in Calc 1. And your book gives you a second derivatives test to use for classifying critical points. This one is a little bit hard to memorize, and I recommend that you spend a little bit of time studying, what this says. And example 3 is a good example of finding and classifying critical points, as is example 4 on the next page. Now, example 5 talks about finding the shortest distance from a point to a plane, and this has the old trick of, instead of minimizing distance, we minimize the square of the distance so that we don't have to deal with the square root in the whole thing. And this is an old trick you might remember from Calc 1. It still works here. Example 6 is another good example. These are all examples that you should work through. There's a discussion here of absolute maximum and minimum values. And you don't have to worry too much about the closed, not closed set thing. We're not going to spend a lot of time on it. But do give it a read. What you should pay a lot of attention to is square 9 over here. How to find the absolute maximum minimum values of a continuous function on a closed bounded set. And example 7 is a really, really great example. I especially like the discussion here of what happens along the boundaries of the domain D. So you should pay really, really close attention to this example. It's pretty instructive. And that ties together the section.